Um, Hello, Anirudh. Can you hear me? Yeah, good afternoon. Uh, I think we can wait for some time for some more people to come. And yeah, if no other come, then I can personally like you can ask me doubts personally that you have, or I can go through an example for parallel manipulators or serial ones, right? Okay. So we will wait. Yeah. Yes. Sure. 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 I mean, we'll wait till 4:05. Yeah. Yeah. I think we can. Yeah. I think we can start now. So, Anirudh, like, are there any specific questions in week 3 or 4 that you would like to ask? Yeah. Hmm. Wait, I think there might be some problem if you share the screen. Yeah. I mean, I think then I'll have to unshare, but I'll try to open that assignment on my end. Yeah. The multiple, these multi, hmm yeah, for Puma 560. Yeah. Okay. Yes. Yeah. Hmm. Okay, I think you can share also, since there is nobody else here. I will stop sharing from my end. Where it is? Yeah. Hmm. Yes, yes, it is. Hmm. Three, right? Yeah. Uh, what are the units that you're reporting your solution in? No, like, are you getting 1.04 radians or degrees? Yeah, that's cool. But then did you convert these angles also that have been given to radians? Like, eh, okay, like, can you show me your solution procedure? How did you proceed with that? Mm-hmm. Yeah, sure. Hi, Kalairasi. Uh, Hi, Kalairasi. Can you hear me? Wait, did he leave? So for Kalairasi and Alagu, uh, Anirudh is telling me, yeah, hi. Is it Anirudh? Yeah, yeah, that's cool. Like, I was just talking to two new guys who joined this session. Yeah. So like, I'm just hearing out his doubt that he had in week three, and like, we'll be taking this session in this way only. You guys can tell me the doubts that you have, and I can try my best to clear them. So yeah, I think you're not uh, sharing right now. No, but is the camera on? Because I can't see anything. No, no, like, I understand, but it is not showing up. Can you check your camera again? Mm, no. Okay, I think you do one thing. You just share again the equations that you used, and you tell me from there what you did. Yeah, yeah, verbally from the equations, we'll go there verbally. Yeah, okay. Yeah, that's okay. Yeah, yeah, I can understand, but mhm. No, no, like I have the problem open with me. Yeah, yeah, that's cool. So you're you're facing problem that the theta 6 that you have calculated is not matching, right? Yeah, and to calculate theta 6, you have used the equations that have been given earlier. Yeah, like, are you sure you're using the correct equations? Because I think the equations that you showed me, they are for like only till reaching the wrist. Those equations work, right? They only give the position of the wrist that you are using, and then yeah, and then you have to use like uh, the rotations after you reach the wrist. Okay, so the correct approach would be wait, I think I'll share this thing. Can you see my screen? Okay, so do you see this slide? Okay, so yeah, so this is, what is the final orientation of the wrist, right? That is depends only on theta 4, theta 5, and theta 6, right? So, like, using this, you have to calculate, you know. So, no, not act, no, 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 because I think those are all variables, right? That you have been given, theta 1, theta 2 till theta 6. Okay, yeah. So what I'm trying to say is what you are using here. Okay, wait. You were using these equations, right? Yeah, so these are incomplete as of now. These are just the translational part. Okay, and they can only give you theta 1, theta 2, and theta 3 at best. Okay, so what basically you had to do, you had to make the complete transformation matrix. Okay, that is T60, right? And then using that, you had to calculate theta 6. Okay, No, wait. Yeah, so see, I think for Puma, you have been given this thing right here, the inverse kinematics, right? So then to calculate theta 6, it is just minus a tan 2 r21 comma minus r1. Can you try this quickly? Yeah, like on MATLAB or on a calculator, any one of them is fine. Yeah, but I think this will only work for this R36, right? But you only also need R03. I'll show you how to do this. Hmm. Yeah, yeah, yes, yes, that is true. Yeah, that is true. Yes. Okay, that is correct. But you see, you have not been given value of any theta. You have been given values for alpha, A, and D. Okay, so what you have to do is you have to construct this T06. Wait, you can't see this. Okay, so you have to construct the complete T06. I will come on the pad. Yeah. So you see, okay, you have to calculate this completely. Okay, and it would have come as a function of, okay, theta 1 to theta 6. Do you understand what do this mean? Yeah, yeah. So no, what does this mean when I say it would come as a function, of theta 1 to theta 6? No, 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 not inverse kinematics, not inverse kinematics. Okay, so you have a DH table, right? And you know how to calculate this, right? You have the formula, right? And you can calculate it also. Okay, so using that, you calculate T60. Okay, like successively calculating T0, 1, 1, 0, 2, 1, 3, 2, like that, right? Yeah, because we write this as this, right? T01 times T12 times T, yeah, yes, till 5, 6. Okay, so you use the DH table, you write these individual transformation matrices first, right? All these individual, and then you multiply them. Okay, so once you multiply them, you get T06. Okay, now in this T06, you try to calculate, what will be, okay, because see, this T06, this will have this form, okay, it will have the rotation part, okay, and the translation part, and then just, a 0 and 1, okay. So in this rotation, yeah, yes, so this has been given to you, but you don't know, how it is related to theta 1, or you don't know how it is related to theta 6, right? Okay, what you have been given is the transformation matrix for a particular value, but you don't know that particular value. That is what you have been asked, right? Yes. Yeah, no, you don't know any of the angles. That is the point. right? So what will happen is this R60, okay, for example, let us say for example, okay, it comes as this C2, C3, C5, okay, or S1, C2, C5, something like this. Okay, this is completely, I don't know what these values will be. Like these, you guys have to calculate. Okay, so somewhere in this rotation matrix, okay, so basically what you had to do is, how did you, calculate inverse kinematics up till this point? Like, how did we arrive at those formulae? Yeah, yeah, but you see, you don't have the value of C2, right? You have the value of this complete thing here, correct? Yeah, so what you had to do is, first using this, your result, okay, you had to calculate what is C6, okay, what is C5 in terms of the terms of the rotation matrix, okay, in terms of, let's say, R00 and R11, okay. Mhm. Yeah, yeah. So, I mean, either you can try to solve some kind of nonlinear equations, okay, or what we can do is we can try to do what we had done in case of. Do you remember what is the matrix that we got in case of Euler angles? Yeah, when we just started doing. Okay, I think now, yeah, that's fine. I think now I have the complete equations for you. Mm, yeah. Okay, so see, for this Puma robot, you know, wait, hmm, R, yeah. So R11 is something like this: C1, C23, okay, C4, C5, C6. So can you open this lecture 7 PDF that was shared with you? Yeah. Okay. In this, you have been given the complete values. Okay. All the terms of the direct kinematics problem for this Puma 360 robot on, I think, page 15. No, no, you don't have to share. You just have to open it. Yeah. Lecture 7, lecture 7.pdf. Yes. Wait. Yeah. Wait. I'll share with you. Yeah. Can you see these equations? Yeah. 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 That's good. But you see, now what you have to do is this. I mean, whatever you have to do, but these equations, okay, these are all in terms of theta 1, theta 2, and theta 3 up to theta 6. Correct. So using these equations, you first have to calculate. what is, let's say, theta 5, in terms of R11, R21, R31, terms like that. Okay. And then once you had the expression for theta 6, okay, you had to plug in values. You get my point? Hmm. So see, yeah, yeah. No, you don't have to make any assumption actually. Like you just have to substitute some terms. Okay, so there is no assumption, but you just have to do algebra at this point. Yeah, like you try, for example, if you square and add the first two terms, right? Okay, so then you'll eliminate theta 1 from these terms, right? Okay, and then if you square and add R31 and R32, okay, then also you will be left only with, terms that only contain theta 5, theta 4, theta 5, and theta 6. Okay, same with R13 and R23. Okay, if you square and add these terms, 1121, okay, 3132 and 1323. Okay, what you will be left with is actually the R63 kind of terms that we were seeing in when I shared previously, right? Okay, so then you can try to calculate, just the theta 6 from there, because now you essentially have three equations with three unknowns, right? Do you get what I'm saying? Yes. Yeah. So basically, if you eliminate these extra variables that you do not need and end up with variables that you will be, finally just needing, finally you will get an expression for theta 6 that depends, that expression will only contain these R terms. Okay. It might be some weird combination of those, but it will only contain these terms. Okay. Then you had to put the values from your, transformation matrix that was given. Yeah, they are coming from the transformation matrix, but we don't know what combination of theta 1, theta 2, and theta 3 they are here, right? Yeah, yeah. So that's why what we are trying to do is we are trying to first get an expression of theta 6 in terms of rotation. Because, when we read about Euler angles, we also, we learned how to make rotation matrix from given Euler angles. But then we what learned afterwards was, given the rotation matrix, how do you extract the original Euler angles? Do you remember that? Hmm. Yeah. So I mean, if I just have had to repeat, so what you do is for the problem, okay, you write the individual transformations from your DH table, right? T01, T12, so on till T56. You multiply all of them. Okay, then what you will get is something like this, what you're seeing on the table, on the screen, right? And then using this, or right, rather than writing those equations, just use these equations, okay, and then try to eliminate the angles that you do not need. Okay, as we discussed right now, okay, that if you square and add some of these values, okay, then many of these will just cancel out directly, right? Then what you will be left with is three equations with three unknowns. Okay, yeah, no, then you can try to reduce there also. Okay, like let's say you then end up with equations in theta 4, theta 5, and theta 6. Then you can try to eliminate theta 4 also. Then you can try to eliminate theta 5 to finally get theta 6. I mean, yeah. No, actually, I mean, you still have to calculate the other two, right? Yeah. I mean, if you have two equations and there are two unknowns, okay, then of course there will be a unique solution, but you will have to calculate the values for both the variables, right? Yeah. So, like, is there any other doubt in this problem? Yeah, yeah, sure. Like, I mean, you just use these equations, okay, that are there on the screen, and then you just try to eliminate every angle, except theta 6. Okay, and this elimination is possible because there is a unique solution for this problem. Like that is why it was given. Okay. So any other doubt in week 3? Yeah, I mean you can ask week 2 also, like there is no problem. Wait, I'm opening it. So the first question. Hmm. Yeah, so what was the doubt in this? Hmm. Hmm. Yeah, yeah, like you suddenly dropped from the meeting. Oh, that's good. Like you were saying something. Continue. Yeah. Hmm. Hmm. No, no, I think what you were doing is like you might be confused what we had to do here. I will just switch to writing. Yeah. Can you see the screen? Oh, you can. That's cool. Okay. So let us say, no, not this. Okay. For any rotation matrix R, okay. Let us say we call this R11, R12, R13. Okay. And like you get the point, right? There will be terms like all over this. R32, R31, and R21. Okay. So now there are different representations of orientation, right? One is the rotation matrix, right? One is, okay, Euler angles. Okay, like if I want to be specific, let us say the XYZ Euler angles. These are all representations, how you represent the rotation, right? And one of those representations is axis angle representation. Okay, so we say, as I'm saying, these are just representations of the same orientation. Then they have to be connected in some way, right? Right. So what does axis angle representation means is that there is a theorem called Euler's theorem that every rotation in 3D space can be represented by a rotation about single axis, right? Basically, to go from any given orientation to any final orientation, you just have to rotate about the right axis only. If you just rotate about that one axis, you're done. Okay, so that is what the angle axis representation means. Okay, so now I'm saying, I also said this, right, that all these representations have to be connected, right? So how is rotation matrix and angle axis representation connected is, okay, so this theta for angle axis, okay, this comes out to be cos inverse of r11 squared plus r23. I'm not too sure about the squared part. Just a second. Yeah, not this square thing. So it is just r11 plus r22 plus r33 minus 1 over 2. Okay, so this is the angle for the angle axis representation. Okay, and I think for n it is 1 over 2 sine theta. Okay, and then I think, yeah, like it is there on the recorded screen also. You can check it afterwards. So this is 2 3 or 1 3 minus r3. Okay, so basically you can derive these relations also. Okay, but this is how these two particular representations are related. Okay, so what you were asked was this. Okay, what is the angle for the equivalent angle axis representation? You were only asked theta. Okay, now if you try to do this, okay, so the trace, okay, so this basically this summation of all the diagonal matrices we call the trace of the matrix. Summation of all the diagonal entries is called the trace of the matrix. Okay, so what is the trace of this matrix? It is 2. Okay, and what is 2 minus 1? It is 1. Okay, yeah. What is cos inverse of cos in? Yeah, it's exactly 60 degrees. Yeah, yeah. So you see, what you were doing was you were not using the relations between the correct quantities that are involved. Okay, so yeah, like you always have to keep this in mind whenever dealing with orientations. What is the representation that you're dealing with, right? Yeah. Hmm. Yeah. Yeah. No, this is not n bar. Like this is a n hat actually, like the unit vector. Yeah, the unit vector. Yeah. So you can get these relations from any book also, like the book by J. J. Craig. Okay. So are you referring to the PDF of that book or like the book written by Ashitawa sir himself? Yeah. So that book must also have these relations in, let's say, first or second chapter. Whatever the chapter is dealing with mathematical prerequisites, that chapter will have these relations. Yes. Yeah, so now actually see, this is a very neat result that this axis angle representation, okay, is directly related to the eigenvector and eigenvalues of the R matrix. Okay, now we knew that they were connected, okay, but this is how they are connected because when you think in terms of transformation, Okay, any 2D transformation. Okay, what do we mean by 2D transformation? Like we represent them as matrices, right? So any 2D transformation can be seen in terms of its eigenvector and eigenvalues. Like what is it actually doing about those eigenvectors? Okay, so yeah, no, no. You see that when you do the transposition, when you do transpose of the rotation matrix, okay, that is basically the inverse rotation that you're doing. Okay, like this is now a completely different concept. Okay, now you're just saying that I went from, let's say, orientation A to orientation B. Okay, now how do I go back from orientation B to orientation A? Right? Yeah. Okay, so now subtracting also means, inverting that transform, right? If I say that this was my transform, okay, and I want to go back, it means I want to invert this transform. Okay, so this inverse is basically what I call, from B to A. Okay, from bottom to up, right? We are going from B to A. Okay, and for rotation matrices, because they are special matrices that are orthogonal. Okay, this we don't have to calculate the inverse. No, no, no. See, it's not a symmetric matrix. It's not even a skew symmetric matrix. Okay, it is just an orthogonal matrix. Okay, so for an orthogonal matrix, the inverse is the same as the transpose. Okay, yeah, yeah, they're like that's good. Okay, so this is what it means to be an orthogonal matrix. Okay, and it's like not just orthogonal, it is special orthogonal matrix. Okay, so like if you do like R into R inverse for matrices, it should give identity, right? Okay, but if you do R transpose for rotation matrix, this also gives you identity, right? Because inverse is the same as transpose. Okay, and if you try to calculate the determinant of the rotation matrix, okay, it is plus one. Okay, now if you calculate the determinant of any normalized orthogonal matrix, okay, just orthogonal, then it can be plus minus one. Okay, but this is where the special, when we call rotation matrices as special orthogonal matrices, this is where the special parts come from. They can only have determinant of plus one. Okay, yes, all not just a positive integer, it should be plus one. Yeah, otherwise it is not a rotation matrix. Okay, and this plus one actually denotes that we are using right-handed coordinate system. Okay, if you use your rotations using the left-handed coordinate system, then you will actually have a minus one determinant. Okay, but like we have chose to not use all those values, right? So that's why like we just say that yes, the ones with the plus one determinant is what we are going to use. Yeah, 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 sure. Okay, yeah, you can come to week 4. Mm-hmm. Mm-hmm. Yeah. Mhm. I cannot see actually. You are only sharing the, I think, the Chrome window. Yeah, it is. Hmm. Okay, so like first of all, do you know what do you mean by the workspace of the robot? No, no, see that is not a workspace. Okay, like from what the term itself says, it is where your tool can move. Basically, the you know part of the 3D space where your tool can reach, right? Or your end effector can reach, right? Because if you'll even consider a 2R robot, okay, it cannot reach beyond the circle of radius L1 plus L2, right? Yes. Okay. So yeah. So you are saying the correct thing, the radius of the workspace. Okay. So for a 2R manipulator, that workspace happens to be in 2D plane. Okay. So you can either try to get analytical expressions for the workspace, as sir has also done in lectures. Okay. Or what you can do is you can try to plot the workspace using any software in which you can plot. Okay. So now how you plot the workspace is, you see, first of all, you will solve the direct kinematics problem for this uh, parallel mechanism. Okay. And since it's a planar mechanism, the workspace should be what? It should be a 2D workspace. I think the mic is very close to your mouth. I cannot hear it clearly. Yeah. No, no, see, yeah, so you see, we don't say it a 2R workspace. Okay, 2R workspace is for the 2R robot. Okay, so I mean we just call it a workspace for a particular robot. When you say 2R workspace, you you want to mean the workspace for 2R robot, but this is not a 2R robot, right? Yeah, this is a completely different. Yeah, this is a completely different kind of robot. Okay, but now to calculate, the workspace of the robot, or to let's say plot the workspace of the robot, what we do is we first write all the relations that are required to solve the direct kinematics problem, or as we also call it, the forward kinematics problem. Okay, then what you do is, because then what are your actuated variables, theta 1 and theta 2 in this case, right? So you slowly vary theta 1 and theta 2 both. Okay, and you see what is the value of x and y, right, for each value of theta 1 and theta 2, for each possible combination, right? Okay. Yeah, so you see, yeah, these are the equations, right? These are all the um, independent equations for the planar loop. Okay, but now I think in the next slide, sir might have written x and y in terms of all these, right? When he has no, yeah. So yeah, this x and y. Okay, so this x and y are the coordinates of the end effector. Okay, so now this, the whole trajectory, not just the trajectory, whatever is the complete set of possible values for x and y should be, all the, you know all the points where my end effector can reach. Yes, exactly. Okay. But if you like take a look at the equations above also, phi also depends on theta 1 and theta 2, right? Okay. So basically what you will have is there are only two independent variables, and that you are saying, yeah, I mean in this case there is only theta 1. Okay. In the problem that you have in assignment, there are two, theta 1 and theta 2. Okay. Now I will like let me just talk about this question right now. Okay. So there is one actuated angle theta 1. No, no, the one that you showed me right now in the lecture slides. Yeah, like I just want to give this as an example, and then we can talk about that, like because this is easier to talk about, right? So in this problem, theta 1 is the actuated variable, right? And everything else, x, y, phi, okay, they are all passive variables. Okay, passive means they are not actuated, but they depend on your actuated variable. Okay, so what you need to do is just for every value of theta 1, you first calculate what is the phi corresponding to that theta 1 using the equation that you must have written when you were doing the forward kinematics problem or the direct kinematics of this manipulator, right? Yeah, so from here you can write all these passive variables in terms of theta 1, right? Right, right. So using all those values, you calculate your x and y and you plot them. Okay, you plot x against y or y against x, however you want. Okay, so whatever is the plot that you will get for all possible values of theta 1. Okay, because we can see, right, this is a non-linear relation. Okay, so it won't be just, a line or a rectangle or something. Yeah, most probably it will be a curve. We'll know when we plot it, right? So that is what you have been asked to do. You now, in that case, now you can switch to the week for problem. Yeah, in this case, you have been given two actuated variables. Okay, and you have been asked about the workspace of this x comma y point. Okay, but you can see there are many passive variables also, like this phi 1, phi 2, phi 3, right? Okay, so what you just need to do is in the direct kinematics, like what is the direct kinematics problem for a parallel manipulator? Okay, it involves choosing the desired or whatever the end effector point that we want to choose. Okay, and then writing the passive variables. Okay, identifying the passive variables and then writing those passive variables and the end effector coordinates in terms of your actuated variables and the given link lengths, of course. Like, yeah, yeah, that's good. Okay, so like, have you seen the lectures about parallel manipulators? Yeah, that's cool. That's good. That's good. Okay, so I will just describe, verbally what actually direct kinematics problem is. Okay, so when we say direct kinematics for a serial manipulator, okay, there we have a well-defined end effector, right? The last point of the manipulator. Okay, so we just call it an end effector. Okay, and we say that yes, the workspace of this end effector, okay, is the workspace of my robot. Okay, because I'm assuming that is the point that will interact with everything, right? Now, in the case of parallel manipulators, there is no unique end effector for many robots, right? Let's say for this case right here, like there is no single point that I can call the end effector, right? Where I say that yes, this is the point that should interact with the environment only, correct? Yeah. So what we do in parallel manipulators is we choose a point as an end effector point. Okay, it is like It's on us which point do we choose. Okay, if you take a look at the lecture slides for that simpler 4-bar problem that sir has, discussed, he has chosen x and y as a random point on the second link. Okay, you can go up and where the figure is there. Yeah, this thing. Okay, so he chose this point on the second link that was at a distance a from one end and b from another end in the second figure. Yeah. Okay. So in this problem, he has chosen this point to be called the end effector point. Okay. And one more thing, there is only one actuated variable in this case, theta 1, right? But like we can see that if you move theta 1, all the other angles will also change, right? Like, like theta 1, theta 2, and theta phi 1, phi 2, and phi 3. No, like the direction can be anything. Okay. But we know that they will change when we change theta 1, and they will not change when I keep theta 1 fixed, right? Okay, so basically their value also depends on theta 1, right? Okay, so those joints that I'm not or we are not actuating, we call them passive joints. Okay, so yeah, so the passive joints are those whose values depend on the actuated variables, but they themselves are not actuated. Do you get this point? Yeah. Yes. Okay, so in this case, phi 1, phi 2, and phi 3 are my passive variables. Okay, so now what we do next is similar to how we define the direct kinematics problem for serial manipulators. Okay, like what was the direct kinematics problem for serial manipulators? No, you don't need to go there. Like I mean, you can go if you want, but okay. So what was the direct kinematics problem for serial manipulators? It was that given my joint angles, what are the position and orientation of my end effector, right? Okay, because once I specify all the joint angles and I have already been given the link lengths, okay, the position and orientation in most cases that we have encountered in this course, they become fully defined. For example, we can see in the example of the Puma robot. Okay, if I specify all the angles from theta 1 to theta 6, the position as well as the orientation of my end effector, it is fixed. It won't change unless I change any of those angles. Okay, so what we do similarly in this case for parallel manipulators, we like in this case the point of interest is defined by us, as I said, x comma y. Okay, but yeah, that's why in this problem you have been given specifically that yes, this is your point that we will call the end effector point, the x comma y point. Okay, like this is the point of interest in this problem. Okay, so now to write the coordinates of this point, okay, we need like of course we need the values of all the variables, right? Because this right here, like this is geometric problem now, right? So the next step for parallel manipulators is to write passive variables in terms of your actuated variables. Okay, now passive variables here are 5, 5, 1, 5, 2, and 5, 3. Yes. Okay, now in this case, theta 1 and theta 2 both are actuated. Okay, so unless both of them, if both of them stay constant, nothing will change, right? Whenever any one of them moves, or even if both of them move, then the configurations will change. And then if I fix them at some other place, then also everything will not change. Yeah. Okay, but you can see that if I move theta 1 or theta 2, okay, then these angles phi 1, phi 2, and phi 3 will change, right? Right. So, but they are not actuated. So, what are they? Passive variables, right? So, what is the next step after identifying the passive variables is to write the equation of passive variables in terms of your actuated variables, right? Get the relation between your passive variable and actuated variables. Okay. Once you have that relation, then you can get on to write equations for your end effector because that equation will involve your passive variables. Mhm. Mhm. No, no, no. See, x and y, x and y are variables of interest, point of interest. Okay, but the passive, like, but see, we have defined them as something, right? We have defined them as our end effector. Yeah, see, it will change, but it can also be represented in terms of theta 1, theta 2, phi 1, phi 2, and phi 3, right? Now we are, yeah, yeah, yeah. So what I'm saying is the coordinates of this x and y of this point that we are denoting with x and y. Okay, the coordinates of this point depend on all the angles. We can say this for start, right? That yes, the coordinates depend on all the angles. Okay, once all the angles are fixed, the coordinates will not change. Okay, but then out of theta 1, theta 2, phi 1, phi 2, phi 3, now we now come to know that phi 1, phi 2, phi 3 also depend on theta 1, theta 2. Okay, so to calculate x and y, I first need to calculate this phi 1, phi 2, phi 3, right? Because x and y depend on all these five angles. No, no, see, hierarchy is x and y depend on all five of them. Theta 1, theta 2, phi 1, phi 2, phi 3. Okay, and the link lengths, of course. Okay, this L1, L2, L3, L4, and L0. Okay, and then your phi 1, phi 2, and phi 3, they depend on theta 1 and theta 2 also. Okay, no, no, theta 1 and theta 2, you are assuming that you have, like, you will give theta 1 and theta 2. They are actuated variables, right? So, yes, okay. So you will give theta 1, theta 2. Okay, there will be some corresponding phi 1, phi 2, phi 3 for that. Okay, and using all those, you will calculate x and y, right? Now you can, if you vary theta 1 and theta 2, x and y will also change, right? Okay, so now we come to the second one, that how do we sketch the workspace of this point? Okay, you can either use MATLAB. Okay, so you will just write all the equations. You will just give different values of theta 1 and theta 2. You'll get different values of x and y, and you'll just plot it. Okay, or what you can try to do is in the lectures, sir has shown an analytical way of driving the boundaries of the workspace of any robot. Okay, so you can go through that approach also. Yeah, I mean, if even if you do it analytically, you should at least verify it using any program like MATLAB or Maple or something. Okay, like, yeah, that will consolidate what you have learned. So, like, any other doubt in this problem? Hmm. Yeah, yeah, sure. I mean, day after tomorrow, my other colleague will take the session, but you can ask him also. No, yeah, but I mean, you can ask him also. Like, he's well capable of answering all the questions. Yeah. Okay, Anirudh. Uh, so yeah, I think we since nobody else is there, I will conclude the session here. You can leave the meeting.